Okay, hello and welcome to my channel. Today we're gonna talk about the spherical harmonics, and we're gonna finish off the momentum, the angular momentum part by getting the finalized Schrodinger equation. So first, we're gonna talk about the spherical harmonics. So this is basically a mathematical concept that is like similar to the Fourier transforms, but it is in like 3D. These gonna take like a shape, so it is mathematical, but like not really, because this is also the solution to the angular part of your wave function, meaning your wave function is gonna be the radial part times the spherical harmonic. Okay, so the formula for spherical harmonic is YLM, theta and phi. This is 2L plus 1. It's very long. 4 pi, 1 minus m, 1 plus m, both of these factorial. This is times root this entire thing, your Legendre polynomial, and minus 1, okay, and EIM phi. So that is the formula to calculate your spherical harmonic. And here your m is only going to take the positive part, the non-negative part of L value. So instead of being bound like by minus L to L, this is going to be bounded by 0 to L only. So non-negative part. Okay, so that is the formula for your spherical harmonic. Now let's take a look at some typical spherical harmonic, the easy ones that you're gonna see. So let's take a look at the y00, y10, and y20. Okay, so why I don't pick, y01 or 02 is because, well, the m part, as I said before, it does something, but it is not as prevalent as the L part. The m part, basically, what it does is that it's gonna rotate the cut that you will do on the spherical harmonic. And the L would be the one that add the cuts. Okay, so y00, there are no cuts, and in space that would look like a sphere, hence the name of spherical harmonic. So, and you see the spherical part already, and where's the harmonic part, you might ask. And this is a ball, and the harmonic part of it is that it would oscillate by sort of imagine a ball, but like it is like breathing, like, so it's gonna inflate and then shrink and then inflate and shrink like that. That is y00, and with y10, it's gonna look like this, like two balls, or two spheres, because you made a cut. Okay, so this is what it would look like, and when you sort of rotate it, it's gonna look like this. So you might have seen this in chemistry, but now we're dealing with its physical properties, so it would be kind of weird. So there we go, we have the spherical part. Now the harmonic part of this, you might think that it would be like this, well, two balls gonna breathe, but not really. What the Y10 does is that it's gonna oscillate like this. It's gonna go from one lobe to another lobe. So meaning that it's gonna look something like this. So evolve through time. So all things gonna transfer to one lobe. Okay. Maybe I can draw better. It's gonna go like this, and then I'm just gonna move back up to your upper lobe. Oh, that is basically it. And I believe I can only draw it to Y10. So with Y20, I'm just gonna describe to you what it might look like. Might not be clear, but I'll try my best. So with Y20, it's gonna start to split. So what it looks like right now is kind of weird. It's gonna have two cuts, something like this. No. Yeah, something like this. It's gonna have two cuts. Middle one's gonna be squished, and now when you take the oscillate part, you want to see how it like oscillates. It's gonna go like this and squish in, and then it's gonna turn something like inflating a football. Well, this football, the oval one. It's sort of like a football, and then it's gonna shrink back and then inflate into a football. Okay, so the higher you go, the more it resembles a rippling motion, sort of like a wave. Yeah. And here, when you rotate it, it's gonna look, well, like this. It's like a flower with like more and more petals, and more dimension, of course. And 3 is gonna have like 3 of this and 3 of this, but one more dimension. So it's gonna be in a sort of cube. So yeah, they have like 4 sides of a cube. That is gonna be Y3. Okay, so I guess that would be it for spherical harmonic. One more thing I want to introduce you to is solid angle. So solid angle here. Okay, what? Wait a minute. It might have got scammed. I just bought this pen. Okay. Gosh. So solid angle, right? What is happening? Okay, so solid angle. What it means is I'm gonna write the mathematical part of it first, since, well, this is the confusing part. Once you can like imagine it, it's gonna be well, a little bit more simpler, I guess. Well, it really depends, since well, this is not that simple in the first place. Okay. Wait, no, this is theta only. Okay, I got confused. This is the cosine theta, 0 to pi d phi. Okay, so this is the mathematical expression of your solid angle, and to imagine it, you might have like already been able to do this. It's like an orange. You cut out a slice from outside, goes all the way to the center. You pull it out, and that piece is your solid angle. So, I'm just gonna draw the solid angle. Square. Something like that. That is a solid angle. Okay, so with the solid angle, when you integrate solid angle of two spherical harmonic, say you have L prime and prime, so two different spherical harmonic. These two has to be orthogonal to each other, meaning that you will get delta L prime L and M prime M. So prime here indicates that they're different, not the derivative. Right, so now from this, as I mentioned before, your wave gonna include the spherical harmonic as its solution. So your wave now is a function of r, theta, and phi. So the radial part I write r, say re of r, and so angular part is of course phi lm of theta and phi. Okay, so now we're gonna put this back to our Schrodinger equation. So now our Schrodinger equation is gonna be minus h squared over 2m, the radial part, the r squared, r psi, plus the angular part, which has already been taken care of by the total angular momentum. So write that down on psi plus v r of psi. That is equal to e psi. Okay, so this is what we have right now. Now we would want to eliminate this thing, and by say times an r to these. Okay, so first expand it and take the r first. So this would be transformed into, you take psi expand into r. So what you get is this term is going to be just re, and re, and re. Okay, so with that we times an r to get rid of this term and get re on every term here. So from this you can get that re on every term over L 2m L squared. Okay, L, you might want to expand it instead. So we're gonna take h bar squared over 2m LL plus 1 over r squared r re v of r re equals to e r re. Okay, so from this, you take u of r to be equal to re, and there we go. This is our final Schrodinger equation to the angular momentum part, the spherical coordinates. Yeah. Okay, so this would be your finalized Schrodinger equation. You would use this in the other problems that is taken in the spherical coordinates. Right, so that would be it for today. Goodbye.